Welcome, everyone, to this month's meeting of the Apple Corps of Dallas. This month, we've got Dr. Ian Berg to talk to us about 3D printers. We've been after this topic for a while, and I think a lot of people are interested in hearing what Dr. Berg has to say, so I'll turn it over to you.
Yeah, hey Al. I will share my screen, get my slides up. Let's see. All right. All right. So happy to be here with you all to talk about 3D printing, something that I have had as part of my life for many years now. So we'll go over a little bit before I introduce myself. The goal for today, understand what 3D printing is, understand the basic principles behind various 3D printing technologies, introduce a little bit into how to find and make 3D models for 3D printing. And as I'll mention in a second, kind of like what I use 3D printing for is biomedical research. So I'll talk a little bit about kind of application 3D printing specifically in medicine, because that's kind of my specific world. So hi, I'm Dr. Ian Berg. I started my life as a mechanical engineer, and that's where I really started working with 3D printing. I spent about 3 years in the pharmaceutical and medical technology industry before going back to get a PhD in bioengineering. That was kind of my pivot into the biomedical research world. So nowadays, I'm a postdoctoral researcher and a course instructor here at the University of Alabama in Birmingham. My research is all kind of around cardiac tissue engineering, but I also do a good amount of teaching regarding engineering design and kind of like student final projects before they graduate. And that for prototyping often uses a lot of 3D printing. And then also I was for a few years now been specifically teaching a course for medical students about 3D printing and 3D modeling in medicine. So honestly, that's what a lot of this presentation is kind of modulated from, is that 3D printing in medicine course. So what is 3D printing? And apologies if anything here is stuff that you all know, you're never really sure what anyone's familiarity is. But 3D printing, I often, when I introduce it, it's kind of compared to what it is and what it isn't. So kind of a classic form of manufacturing is formative printing or formative manufacturing, right? So this is injected molding or even metal casting or vacuum forming, bending and rolling, right? You have some kind of form and then you force material in and then it takes that final form. Then there's subtractive manufacturing, right? So that's like routers and lathes where you, I lost my view of all of you.
You can't see us anymore?
Yeah, it was my fault though. Let's see, view. There we go. Oh, now I'm not seeing, oh, sorry, my screen. There we go. Okay, much better. If anyone has questions, feel free just to chime in whenever. Sorry. There we go. Okay. Sorry, I can't advance my slides. Let's try this one more time. There we go. Okay, so 3D printing is kind of the fancy term for it is additive manufacturing, right? So basically, instead of forming something from a molten version or subtracting from a solid block, it's your additive manufacturing is you're adding layer by layer to kind of build up something from the ground up. That's 3D printing at its base. 3D printers come in many shapes and sizes. I tried to look up if the library that y'all are at right now has some 3D printers, but I couldn't find online. But my guess is that probably many of you run into 3D printers that kind of look like these out in the wild, schools, libraries, etc. But they come in much larger, much more expensive versions, kind of industrial scale 3D printers are also out there in plenty of uses. So this is kind of the general 3D printing workflow. So kind of going from, the cool thing about 3D printing is you can very rapidly go from an idea to a physical object. So when you have an idea, you start out by creating some kind of digital model. That's kind of the CAD software, computer-aided design software. Once you finish your designing, and as we'll talk about, this is kind of the hard part, right? The hard part of 3D printing is designing what you're going to print. Then you convert it to kind of a universal 3D model that lots of different types of software can understand. You send that to what's called a slicer software. It kind of converts that 3D object into those additive layer versions that we just saw introduced. And that also creates a set of printer instructions. And ultimately, you go to the actual printer, and then you have a 3D object. And so we'll go through most of these steps in a little more detail to talk about them. So digital model. This is what, whenever I'm teaching my students about 3D printing and prototyping, this is what I always tell them, that kind of like the bulk of work in 3D printing is this stage. Like if you do your job right, hopefully you just hit go and the print is created. But doing all this design work, at your computer and some kind of software, that's where the real work is for 3D printing. So typically you're going to use some kind of computer-aided design software or CAD software, and this is going to be kind of a fully defined geometry, but the types of files and how they define the geometry is really going to depend on the software. And we'll talk a little bit more about software choices in a bit. Once you have that digital model, you have to convert it from that very specific kind of software version into something that kind of the printer softwares can understand. And so in that stage, you're going from this kind of fully defined geometry into a mesh approximation, right? So if the circle is kind of that original CAD model, a mesh file is kind of built up of all these individual lines or triangles that kind of approximate the real geometry with this kind of mesh version. And the most common kind that you're going to see is called an STL file. So like if you're out online looking for, like a cool phone case, it's very common that you're going to download directly this STL file that can go directly to the printers. And if anyone's kind of does any kind of like graphic design, it's very similar going from like a vector image, kind of these fully defined images, to a bitmap, right, where it's like pixelated. This is kind of like the going from your CAD model to your STL, your mesh file is very similar going from like a vector image to the pixelated bitmap versions. So once you have your STL, your mesh file, you're going to need another piece of software, which is the slicer. So again, the slicer converts that mesh file into something that the printer is going to be able to understand. So kind of the first step is it takes the 3D version and it creates a bunch of different slices kind of in that Z dimension. And then once it's created the sliced version of the model, it then generates the literal instructions for the printer. This is kind of called the toolpath of the G code. So if anyone has worked in their careers with like CNCs or like other kind of computer controlled like lathes or mills, it's very similar to that. It's converting that layers of slices into literal movements of the nozzle, as we'll talk about in a second, to actually print the object. Slicers are, much like the CAD, and the printers themselves, they come in a lot of different shapes and sizes. Some slicers are proprietary, but there's also lots of kind of like open source and general purpose slicers that work with many, many different types of printers, especially in kind of the small scale hobbyist ones. And again, this is kind of the other place for you, the designer, the 3D printer, to kind of have a hard part where you have to think again. You'll decide things like the layer thickness of the slices, the orientation of how you want it printed. We'll talk about how certain things can't just be printed as is. They have to be kind of added features to help support them or make sure they're printing correctly. And so that's kind of all in this step, as well as material parameters like the temperature that certain components have to be at or like the speed that it's printing at. So again, this is kind of another place for you, the designer, to have to think and understand how 3D printing works. But that then also brings to printing. And hopefully this is the easy part, right? So the 3D printing is all in the setup. If you've done your job, you've made your CAD file, you've made your STL, the G code, now you basically just hit go and it'll print itself, and we'll go over the types of printers next. And then finally, once printed, that part might be ready to go, or there might be some post-processing. So you might need some cleaning or curing depending on the technology, removal. So this is an example of like supports that had to be printed in the way that you oriented it. So there's going to be some removal of that, some sanding or polishing, coating or painting. But you've now gone from idea to physical object. Maybe before I keep going, any questions about kind of the general workflow of 3D printing?
Hmm.
What software do you make in the digital model?
What was that?
What software do you make in the digital model?
I muted myself.
Hold on to that for 1 second, because I will go through recommendations for software, because that's a great question.
Wait a minute. Oh.
Let's see. So next, we're just going to run through kind of some of the most common 3D printing technologies, because different types of printers work in different ways. So kind of the most common that I think you'll see, especially like when you're out at libraries and schools and things like that, is this method, the fused deposition model, the FDM, or sometimes called fused filament fabrication. So in this version of 3D printing, you have a spool of plastic filament that's kind of led into the printer. It is pushed through a nozzle. That nozzle is heated to a desired temperature, and a motor is going to push the material through the nozzle, kind of extruding it like you would in any other extrusion process. And then the nozzle is going to move in the X and Y direction to kind of draw out, using that nozzle, a single layer of the 3D print. Once it's finished drawing that entire layer, then that platform is either going to move down, or the nozzle could also move up in the Z direction, and it's going to repeat that again and again. And so again, this is probably the most common type of 3D printing that you run into, or when you hear 3D printers. There are different versions of this. Some printers can have multiple materials by having multiple nozzles or automated switchers to move that in and out. And so when you're doing this printing, some support structures are needed, right? So there's from a book that I really like, it's kind of the T, H, and Y rule. So like anytime that you have these overhang areas, if you were just to lay down that molten plastic, it does solidify quite quickly, but not quickly enough just to float in the air. And so for that reason, you have to have those supports present. So when we saw the post-processing, that was the reason. Anytime you have overhangs over a certain angle, you have to build out supports so that they're not floating on nothing, or else you get kind of this spaghetti in those floating areas while you're building that out. As I mentioned, some printers can have multiple materials by using multiple nozzles. So kind of in this animation here, you see it has a red and a green that are both fit in to nozzles at the same time. There's also some really cool printers nowadays that have like a machine that just flips in and out the nozzle at any different layer. And the materials you'll use with these is kind of any thermoplastic polymers. It has to be some kind of plastic material that can be melted at a relatively cool temperature. I mean, we're thinking like, 200s of degrees Fahrenheit. So hot, but, not insanely hot, but then solidifies. So common ones we'll run to is PLA, PETG, ABS nylon, and there even are kind of rubbery materials like TPU, the rubber material that you can get a filament of and go through this process. So I mentioned you need the supports for the overhangs. The other thing about 3D printing in this version is it's very, very rare for you to print things 100% solid. So you could, if you wanted to, you could print 100% solid each layer, but for the most part, you don't need to. That's just wasting a lot of time and material because these pieces are likely to not be fully structural anyway. So when you think of the solid parts of your models, you're typically going to have some percentage of the infill kind of filled in by that extruder nozzle, as well as certain patterns. So different patterns have different speeds, have different strengths, people have different favorites. But anything from like spirals to honeycomb are like kind of actually what you'd see if you cut open one of those 3D prints. And then again, you can also set how dense of the infill that is. And that's going to affect things like both the time it takes and the amount of material it takes to do the printing, but then ultimately it also affects the strength. So it's all about, is this just in the shelf and look cool, or is this actually supposed to have some kind of like structural element that you need to achieve? And so that's kind of, again, your choice as a designer, usually in that slicer phase, that kind of like you give it the mesh and then you tell that slicer software for its instructions what you want it to do with the inside. This is what they look like again. So like you're probably likely to run into things like this, kind of these desktop ones. But then there also are, these enormous high resolution multi-material printers here. So, things here run any from like a couple $100, to many, many thousands of dollars for the same technology, obviously, with different versions of the same technology. So again, pros and cons of this particular technology: relatively inexpensive and common. That filament is easy to obtain and handle. You order it on Amazon, it comes. You don't have to wear gloves or anything to touch it necessarily. And typically there's not a lot of post-processing. You might have to break those supports off of your final part, but then you're pretty much ready to go. There's no curing or chemical reactions that need to occur. But the cons of this technology is generally poorer kind of like resolution than other technologies that we'll talk about. You'll have rougher layers, more visible ridges. Very clearly has been 3D printed. And for the most part, you have kind of weaker, less robust parts. So, it depends what you're doing this for. If you're trying to prototype it like a functional object, there's a good chance that this won't be good enough. But for things that are really just all about look, aesthetic, and kind of to achieve like what you want to achieve looking at it, then often this type of 3D printing is plenty advanced for whatever you want to do. All right, so the next one I'll introduce is kind of the general term for it is vat polymerization. Again, kind of like the last one, there's different kind of subcategories in this. Stereolithography versus direct light processing versus LCD stereolithography. But the whole premise with all these technologies is instead of having that solid filament that melts and then solidifies, instead you start out with a vat of liquid polymer. And that liquid polymer is photosensitive. When it's hit by light with a certain wavelength, the liquid has a chemical reaction and it polymerizes into a solid version of itself. So that's kind of the premise of all the technology. And then really what kind of creates the subcategories of this is just what is controlling the light to ultimately polymerize only the areas that you want to, right? So the whole cool thing with this type of material is it only turns into a solid where the light hits it. So in one of the technologies, stereolithography SLA, you have a series of mirrors kind of aiming a single laser beam, and that laser beam basically draws out an entire layer, kind of akin to how the nozzle drew there. Here it's a point of a laser beam drawing in a layer. And then again, you'll have a movement in the Z layer to go from one layer to the next. The other kind of overall parent version of this is DLP and LCD. Instead of having a singular laser point and drawing it out, it actually flashes an entire kind of cross-sectional photo of whatever you're trying to make, kind of akin to like a projector on a screen. So instead of having one point, it projects an entire cross-section of one layer. All the area the light hits polymerizes, and then again, it moves in the Z direction and creates another layer. Here, I had two slides, I guess. So kind of the materials here, there's a lot of variety in these materials. For the most part, materials used in these vat polymerization 3D printers are very proprietary because they're really specially made for this photopolymerization purpose as opposed to just melting a plastic. But kind of in general, they're photopolymers. So kind of anything that you could create in liquid form that has this kind of chemical property where if you hit it with UV laser light, it'll turn to solid, in theory could be used with these 3D printers. Again, this is what they look like in the wild. For a long time, there weren't really kind of desktop hobbyist versions of these, but those have grown in the past like 5-10 years. And so you might run into kind of these desktop units at like a library or school, et cetera. But then there also are definitely kind of these industrial scale vat polymerization printers that are definitely in use. I don't know if no one in the chat, am I getting questions or anything? I'm just seeing.
So the cost of these kind of things, is this a lot more expensive than the other one?
Yeah, so we'll go pros and cons. So the pros are these are generally very accurate. You get like smooth, finer details, and you can also have a variety of materials, including, and this is kind of relevant for my research, you can get kind of high temperature resistant materials since they don't have to be meltable at 200 Fahrenheit. You can have materials that withstand high temperatures like an autoclave, but in general, they are quite a bit more expensive than extrusion printers. And also the materials for them are generally more expensive than the spools of filament. Other kind of cons is only one resin can be printed at a time. So like you can't have that multi nozzle kind of property. And then also in the post-processing, so after you print a vat polymerized part, you typically have to wash it in isopropyl alcohol and then put it in a UV curing and drying chamber for like an hour or so. And so you also kind of have to have these other steps in your post-processing. And like I said, definitely more expensive. Now, so like this is kind of the state-of-the-art desktop printer. I told you those filament printers, you can get a good one for maybe a couple $100. This one is like a $6,000 printer. But like I said, these kind of newer technologies have made this quite a bit cheaper. So this middle one here, like a decent version of it, I think is like $1,000 or so. So there are affordable version of this, but you're still like 1,000 versus like a couple hundred for like the desktop hobbyist ones. And then obviously
One of the things that I buy on eBay are little gears for a hobby of mine. They're about a half inch in diameter, and the teeth on the gear are extremely small. And I look at this thing, and it is great. I don't see any ridges. I don't see any artifacts around it. Is it using this method, or could it be using the previous method?
Very likely it is one of these vat polymerization. The other technology that it could be, so we'll pin in that, we'll come back to it, is this last one is powder bed fusion. And so depending on the material of that gear, there is a good chance that it's this version. So kind of the difference between this one and the last one is they're very similar. They typically use a laser, but it's kind of almost like a meeting between the last two that we've introduced. So this one, powder bed fusion, has names like selective laser sintering, direct metal laser sintering, selective laser melting, electron beam melting. But in this one, instead of having a spool of plastic or filament or a vat of liquid, you have a bin of powder. And so that bin of powder is sitting in a vat, to just below its melting temperature. Let's see if my little GIF can run. Here we go. So then you have this, a blade or a roller comes out and kind of like rolls out a very thin layer, and then a laser beam scans the surface, and instead of doing that photopolymerization, it actually melts or sinters the little bits of the material to each other, kind of fusing them instantly in a single layer. And then again, just like all the other technologies, the vat moves down or the laser moves up. And so this one, why I mentioned the gears, there's a good chance that exists. So you do get very high resolution, similar to the stereolithography printers, because they're based on points of light as opposed to physical movement of a nozzle. But this is also kind of the most popular for printing functional prototypes, like things that have to be very structural, because you can print a lot of different plastics, including nylon, which is like very rugged. So it would not shock me to hear that like those gears, if they have to hold up to whatever you're using them for, are like a nylon or like a similar, more robust plastic, printed solid in this way. So my guess is those gears are probably coming from either the SLA type printers, the vat polymerization, or these powder bed fusion ones. The other really cool thing about this technology is you can actually 3D print metal with it. So like instead of having little bits and tiny particles of plastic, you can have tiny particles of metal. And then the laser is basically flash welding those metal bits together. And so you can actually 3D print in aluminum, stainless steel, titanium, cobalt, and chromium. So afraid if I get orthotics are actually 3D print, like custom orthotics, like hip implants, knee implants, jaw implants are actually 3D printed out of metal using this technology. This technology, like I said, it's very cool. You can get ones that are probably feasible to run an eBay business to spend gears, but you're unlikely to do this as a hobbyist, because even this kind of pseudo desktop one that I found from Formlabs, that's still like a $10,000 3D printer, and everything else is kind of up from that in 1 or 2 orders of magnitude. So an amazing technology that lets you 3D print metal, but this is still very much kind of industrial scale technology, less likely to be the home hobbyist printer.
I'm Lawrence, and the question I'm asking is that you work in the medical field, so I take it that you create different things to go in the body at the time of surgery. What type of material that can go in a body that doesn't get rejected, and what do you use?
Yeah, that's a great question. So I personally don't make any implants, but that's a big thing that we talk about kind of in the 3D printing applications class. Is you're totally right. Like things for the human body have to be made very specifically. There's not a ton of certain plastic. It's really all about nuance. So metals, there are a variety of metals that are biocompatible. I think like stainless steel and chromium are big ones. Don't have my word for it. Depending on the application, they might directly get used as like a metal part, but there also might be like a coating that goes on them. It's kind of like a silicone or a Teflon that prevents biofilms to form. But then also same thing with the plastics, is there are certain materials that are rejecting the body. And then like we talk about kind of the proprietary materials, especially with the vat polymerization, there are quite a few proprietary biocompatible materials, they're called. 3D printing is very popular in the dental space. So there's a lot of kind of dental specific materials. And it really comes down to just chemical properties and testing. So if you wanted to make something for the body, you'd go and you'd find, dental material 653, and you'd see all the testing that it's done for things like toxicity in the body, biofilm formation. And then it also depends if it's going to be there temporarily, forever. That's kind of a whole biocompatibility testing piece. That's a very important part of material collection. And that's where you also end up in kind of expensive proprietary materials. Because not only do they have to be compatible, they have to be certified compatible too, right? So like every lot has to go through correct testing, and that testing has to be documented. I think I see a hand also.
Thank you.
No other question? Okay, I'll keep going. I saw a hand, maybe Paul, but
Question.
oh, sure.
I've sent you a message.
Gotcha, in the chat.
All right, and evidently you can simulate neural networks with 3D printers and study them. And if you're supporting the medical field, maybe you know something about that, or you're going to find out something about that in the future.
I have to look at it. I don't know that application off the top of my head. I definitely believe it. It depends. Like anything else, like a 3D printer is very much a tool, right? Like it's, like a scalpel or a pipette or anything else. Is like, it doesn't surprise me that it can mix its way into something like a neural network technology. I'll have to look that up for you.
Okay.
All right, I think we're in pros and cons of the powder bed fusion. So pros of it, no supports needed. So because you're kind of floating in that powder, you typically don't need supports underneath it, which is cool. In general, parts can be much more stronger and robust than other methods. So again, those gears that we talked about, it's a way to make very functional materials. And again, you can 3D print metal, which I always find incredible. But the cons are that printers are much more expensive than the other technologies we talked about. And also in general, the materials are more expensive and harder to source. It's just a much more specialty application. Let's see. So benefits of 3D printing. Its rapid prototyping has also been like a common synonym for 3D printing, but it's because it is so quickly. You quickly go, we showed our workflow from digital design idea to a physical object, basically kind of in one continuous step. 3D printing is quite accessible, especially nowadays, relatively low startup, especially for certain practical technologies. You can do benchtop fabrication, right? You can go to a library and use these now. And right, it's especially great for students because they can kind of make their ideas into real life, avoiding the need for heavy machinery that can be unsafe or expensive, et cetera. And also kind of almost any geometry is possible, right? Kind of really is, with the right tweaking, kind of anything you can design digitally can likely be printed in some way by some 3D printer and very customizable. I always think it's important to highlight the limitations of 3D printing. I always joke with my students nowadays that like no one knows how to use like a drill and a saw because they just want to 3D print their ideas. And I laugh at them when they come to me in class and say, oh, I 3D printed this, rectangular sheet of plastic. I'm like, guys, we can go to Home Depot, we can buy a sheet of plastic and we can cut it with saws, right? Like it's just a tool. We should apply it correctly. But along with that, there are limitations of 3D printing. Is again, depending on the technology and application, there's a good chance what you make is not fully functional. It's more of kind of a representation of the final product, not the fully functional variety, especially if there's structural elements at play. There are material limitations. So again, if you have applications that require high temperatures or lots of like corrosive chemicals, it can be limited or impossible to find a material to fit that. In general, right, if you're more of a manufacturing like this, it's still relatively slow production, right? So when you compared formative and subtractive manufacturing, there's a good chance that our additive manufacturing is relatively slower. Which for us, the hobbyists, might not matter. But again, when the reasons of this, there still is all those other manufacturing technologies on the industrial scale. In general, kind of the cost doesn't drop with scale, right? So the thing about like injection molding is you spend $100,000 to make, your giant molding setup, but then with every 1,000 parts that you make, each one of those gets successively cheaper. Not so much the case of 3D printing, kind of the upfront cost of the printer, and then you're sort of with that. And the other thing, right, when I talk to my engineering students that are trying to create something that would get manufactured later, is when you rely heavily on you might miss kind of those manufacturability considerations. If you're not doing any of the physical manufacturing, the computer and the machine are, you might make something that would be very hard to get manufactured. And then again, there might be other tools for other applications that are better than 3D printing for that. There's been some great questions, but I'll pause for a second just in case anything else popped up. What I was going to come back to is kind of I talked about the real work of 3D printing is those kind of first 3 steps, kind of the digital design piece of making the model and converting it. So we'll talk a little bit more about those now.
So just I'm sorry, I don't know why such feedback, but on the computer that I buy on today, all those floppy that we had on Mac, even well, not the Apple II, but the Macintosh on a Mac II, all those floppy drives have started to get one gear inside that it just, I don't know why all the gears around it are okay, but this one gear has degraded to the point that it turns much. So all of the floppy drives stop working. I'll bet you can fire up Mac SD or SD30 or Mac 2 will have floppy drive. So this one gear that now you can get these really high-tech 3D printers cost you to buy 4 of them $10. So to me, that's cheap. It's a 10-minute fix works. It's amazing. 99% of the problems on floppy that one year. So it's really a boon to me. And I would buy a machine to do it myself. I buy off eBay, really cheaply.
I love that. That's super cool. I only caught half of the talking there, but I love that you had this very Apple Core specific application of the 3D printing. That's really cool. All right, so my guess is that, right, like if you all want to start experimenting with 3D printing, there's a good chance that like you're not going to necessarily get your own 3D printer. You're going to go to a library, a makerspace, et cetera. And so hopefully they'll be able to provide a lot of great help with kind of the physical side of it. But again, I think it's all in the prep. It's all in the kind of preparing or obtaining a model. So one way to get that digital model, either in its CAD or its mesh format, is just to go online and directly download models. And so I'm happy to share these slides. That was kind of my intention. So I just dumped a whole bunch of links here, things.com, 3D printables. There are even kind of, especially in the medical world, there's like NIH-hosted websites with like anatomical models and stuff like that. So you can go online, you can search for floppy disk gear, or you can search for, phone case or what have you, and you'll find all kinds of existing models that you can then bring, skip kind of the CAD step and go straight into the slicer and 3D printer instructions. And so kind of sky's the limit on what people have created and freely share for others to use. Then the other common thing is to create it yourself in some way, and that's the CAD part, the computer-aided design, or back in the day, computer-aided drafting. So these softwares make 2D and 3D models. They're used to generate the geometry that you want to 3D print, and there are lots of software options. Some of them are free, some of them are very expensive, some of them are everywhere in between. So what I usually recommend is that people start out with this totally free one called, we'll come back to this, called Tinkercad, and then eventually progress to Autodesk Fusion 360, and I'll introduce both of those. I know I have a Apple audience, and historically, there has been not a lot of great cross-compatibility between these makers of 3D CAD software and Apple computers, but the two that I'll introduce are totally compatible. One of them, actually both of them, can be run 100% just online in a browser, so you don't even have to download anything. But then Autodesk Fusion 360, which is what I mostly recommend kind of as the next step in CAD, is 100% Apple compatible, which is great because that didn't always used to be the case. So kind of like 3D printers, CAD software kind of falls into a few different main categories. So kind of parametric CAD is kind of the classic engineering CAD, where you draw things in 2D and kind of do different operations to then extrude or extract that geometry into 3D. This is kind of like, when I went to mechanical engineering school, that's what they're teaching us, from day one. And that's what like a lot of the classic like mechanical type engineers will use. Another kind of parent category is solid constructive, where instead of kind of drawing things in 2D and turning them into 3D, you kind of have these sort of basic different geometries like boxes and balls and spheres and diamonds, and kind of you add and subtract them together to ultimately create the thing that you want to create. And that's actually what we're going to, I'll introduce you to today. And then the other parent category is kind of direct modeling in 3D. So like almost like starting with like a 3D something and then kind of molding it digitally, almost like you would clay. And so this is kind of the type of 3D design that's more classic to like 3D animation. Like, so if you want to, make a Pixar movie, there's a good chance that you're going to use a type of software that is kind of this direct molding. And nowadays, like a lot of these are all brought together in software packages where kind of people are trying to take the best of both worlds into one piece of software. But even then, there's probably going to be some kind of primary approach that the software is based around that probably fits into one of these categories. So I always recommend that people want to get into modeling their own stuff, right? Kind of the easiest way to get into 3D printing is to go just directly download a model, either download directly a CAD file, but even more likely just directly download that STL file, just download that mesh file that then the slicer software can directly take in. But then if you want to kind of take that next step into doing your own design work, I recommend starting with Tinkercad for several reasons. One is 100% free, so no monetary commitment if you want to, but it's also fully online. So you open up your Safari or your Chrome or what have you, you go to tinkercad.com, and all of it runs inside of that web browser. So it's compatible with any computer. It's even compatible with like iPads. And so you don't have to worry about compatibility issues or downloading or drivers, etc. It's not the most powerful or precise like engineering focused software in the world, but it's a really great way to kind of get into the general concept of 3D models, also mocking up ideas. Importantly, you can directly export from this online software into that STL type file for 3D printing. And it also has like fun tools, to make like keychains and name tags, just kind of like great places to get started with 3D printing, maybe before you're printing those metal hip implants that we have to do biocompatibility testing on. And it uses kind of a simplified constructive solid geometry method for models. So another great thing about it is there are lots of tutorials even built into the software. So I'll send you this link here. If you go on, you basically click one of these tutorials and it'll actually kind of like show you where to click to like do the modeling. So sort of place a box, it'll sort of show a shadow of the box and show you where to click and drag it in, and really build your skills up from the ground up pretty quickly. But then also on top of those Tinkercad provided tutorials, there's lots of great YouTube videos. So I picked a handful out that seemed well reviewed. That you can also walk through on it, because really the best way to learn these software pieces is just to try them, just to do them, and to do them with tutorials is usually the best way. What I always tell my engineering students, especially, is kind of a great way to learn 3D printing. Once you've done maybe some tutorials, is basically do reverse engineering. Is to take some object that you physically have, you can physically manipulate, and all the dimensions of, and then just try to replicate it in your 3D software of choice. So I often have my students start out with Lego. Something they're very familiar with, is something they have the measurements of. They can physically have it in their hand while they're doing this modeling. And so this is kind of the example that if you think about a Lego, these kind of basic geometries are what you add together to create that Lego, right? So kind of a rectangular prism base, we're adding on kind of those pips, we're adding on those bottom pieces, and then here are kind of those slash fill, those are subtractions. So those are kind of like holes. So everything in orange and red gets added, and then everything that's gray gets subtracted. And when we align those in the right way and kind of group them so that the right things get added and the right things get subtracted, you end up with this Tinkercad Lego. And so I also linked you a nice little YouTube tutorial to make the Lego if you want to. So if you enjoy this and if you learn it, I think the next thing that I usually recommend people go to is go to Autodesk Fusion 360. And so again, very importantly for this crowd is it's totally compatible with Apple products. Also, much like Tinkercad, you can download your Fusion 360 and run it on your computer. But if you have an older computer or something, or you're away somewhere, you actually can run it fully in the browser also. So you can kind of have like a virtual online version of the software that you can run from any computer, even if it's not your own, so you didn't have to download the software. As far as I can tell, at the moment, there is a free hobbyist version of Fusion 360. They've kind of gone back and forth on letting people have free versions or not. As far as I can tell, there is kind of a limited function, but I think totally functional for what any beginner modeler would want, version of 360. And then what's also nice is this software kind of has some of those pieces of the other types of software, like direct modeling and additive and stretch contraction. And so it can do your CAD, it can export your 3D printed model, and it can even bring back in mesh files and work with them. So like if you found something online that was a mesh file already and you wanted to say like add your name to it or, you know, make it like a little bit bigger for some application, is you can actually pull in those mesh files and do some edits on that. Kind of classic CAD software would not have been able to do that. So again, it's kind of having multiple components into one world.
So I don't have a 3D printer yet, but I do have this. I've got that hobbyist version he's talking
Wonderful.
about, and I've used it to design a case for something, and it actually is really good.
Yeah, nowadays this has really become my favorite one. You know, the thing of like, you know, if you're really becoming like an engineer and need to know CAD deeply, you can really start with any software, and then like the skills you gain from that should transfer from Autodesk to SolidWorks or 3D system products. But for anyone learning, I've yet to kind of be more impressed as for like a learning and education product. And the other great thing that other companies don't do is, so there's the hobbies version for free, but also like every student can get a free student license. And so that's also great. And so like the schools don't even have to like kind of do the IT work to get these versions. So I think it's great. So what I use, so this is kind of the parametric workflow that I introduced briefly. And so as opposed to kind of like bringing directly a box in, if you wanted to make a box in parametric modeling, you draw a square and then you extrude the square into a box. And you kind of do those 2D into 3D operations again and again and again. There might be some kind of direct 3D objects, so you can do like a fillet or on a corner instead as kind of a direct 3D, but a lot of it is kind of like defining planes and drawing over and over again. And so what I have my students do is I first make them draw the Lego in Tinkercad, and then I make them draw the same Lego in Fusion 360, and they can see kind of the pros and the cons of both. It's like when you get into like the Fusion 360 type products, you can do a lot more precise work, but in a certain sense also like making the same thing might actually have more steps and be more complicated to make like a simple model. So again, I try and highlight the differences between them, what they are good at, what they're bad at, and then also to learn more. And so I like this. I found this on YouTube is a guy that had put together like a 30 set of lessons in Fusion 360. So if you wanted to go from total novice to somewhat expert, his video seemed like a really good set of them. But then I also pulled in from him, he had a Lego tutorial. So if you wanted to, you can go through that same exercises, make your Lego in Tinkercad, and then make your Lego in Fusion 360, and then again, kind of like see the differences and stuff like that. And then finally, just quickly run through. So slicers, again, there's lots of free open source ones that are compatible with lots of different printers. You know, if you got a 3D printer, you figure out which ones are good for you. If you're using a 3D printer at like a library or makerspace, you probably consult with that 3D printer operator to find out which slicer they recommend and what the appropriate settings are for that particular printer, because that will matter. But again, for the most part, like a hobbyist can use these open source free software. In the VAT polymerization world, some of those are more proprietary and specific. But the two that I run into the most, that people seem to like the most are the Orca slicer, which is compatible with Apple, and then also the Prusa slicer, which is compatible with Macs. But there are a whole host of them. And at that point, right, that's where the universality of that intermediary becomes important, because the particular slicer used might be specific to the printer. I think that's kind of the end of my general 3D printing. Any other questions that have popped up, maybe especially about like the CAD and stuff like that? And again, I'm happy to send off these slides for all those links to be shared and for those tutorials and things like that.
Are you going to talk about your particular use of 3D printers?
Yeah, so I will talk a little bit about mine, my uses, and also just in general 3D printing and modeling in medicine. That was kind of my last little bit here that we'll run through.
Okay.
So when I teach my students about 3D printing in medicine, I kind of, again, I get to do a lot of categorization in these talks. These are kind of the broad applications that I have found of 3D printing in medicine. So the first is kind of like the one that really applies to kind of 3D printing in general, but sort of just prototyping and creating physical objects, so kind of broadly medical devices. But then also creating and printing anatomical models, either for direct use or often for training and simulation. My world is more here, actually, the tissue engineering piece, which we'll talk about, is kind of using 3D printing to make specialty objects that allow for culture of cells and tissues, growing cells and tissues in a dish, as opposed to in a live organism or person. And then also there is kind of the budding world of 3D printing drugs and pharmaceutical products that is a little more niche, but I have run into a lot of academic papers, at least on these. So first category, medical devices. So kind of just like any designer of any product might want to prototype different options. This is very, very true in the medical device world, and this has been very powerful to that industry to much more quickly make your idea and get physical objects you can try. With the advent of these materials that are biocompatible, you actually can directly print objects that are suitable for contact and use with a person. So you can actually, especially in like an investigative stage of research and development for a medical device, you could really make an operational medical device. Here it's like a syringe or an auto injector, which is very cool, but also, you might just be making different iterations of what you want to know if it looks like, or if you want to hand a surgeon like a particular, surgical instrument, even if they can't physically use it on a patient, right? They can feel what it feels like in their hand, and that doesn't have to really have any particular mechanical properties. Especially in the COVID times, people use 3D printers directly create personal protective equipment, PPE. So people have 3D printed face masks, N95 filter holders, all kinds of things. And so there are still people that use 3D printing to directly create objects like PPE. Prosthetics is a world where 3D printing is definitely used. That full customizable aspect of it lets you make prosthetics that have any look and feel. And again, with those stronger materials like the powder bed fusion, you can make prosthetics that are strong enough to be used. And then this sort of pulls us into the next slide in the anatomical models, is that you can directly 3D print patient-specific implants, right? So whether these are stents, or it's very popular in like the dental repair world, you can directly 3D print either molds to make dental implants of it, or you have those direct reusable materials, you can directly print dental implants from specialty printers, things that fit into spines. In the world of kind of facial reconstruction, that's a huge application in the medical world for 3D printing, is to 3D print direct reusable, likely metal implants to repair like the jaw and the skull. So in the world like oral and facial surgery, there's lots of people that are using 3D printing to make these specific implants and repair pieces. And that kind of, sorry, some have been. And so for kind of the patient-specific piece, that kind of fuses us into this anatomical model piece. So we haven't talked about this a lot today, right? So in that kind of world where you get 3D models for 3D printing, we had the CAD and we had the direct downloading, but in the medical world, there's kind of like one more piece that is a common way to get 3D geometries for printing or for modeling, and that's actually to actually use scans that you go to the hospital and get. So like CT scans and MRIs are 3D scans of some portion of the body. And just like doctors can look at that in 2D and 3D to look at what's going on, you can then have more specialty softwares to bring in that scan data and actually convert it into a form that is compatible with all these other 3D printing softwares that we talked about to 3D print a model of a particular geometry. And again, when it comes to the specific implant, they are likely kind of taking like a full MRI or CT and then designing that facial implant or the specialty stents to fit into a heart, or a big application that's also to do like training and simulation or preoperative planning. And so you take your 3D print, you take your 3D scan, you 3D print, the particular part geometry, and then a surgeon can actually practice or kind of look through like where they're going to be placing a stent or doing a surgery. So both for training new students and residents, but also for kind of planning for a difficult surgery, as 3D printing has become more and more of a tool for that, to be able to physically interact with that geometry, before it's the live version on a surgical table. And this is kind of that process where you have some kind of data acquisition, usually like a CT scan or MRI. You do this process called image segmentation, where you tell a computer what's bone, what's lung, what's heart, et cetera. And then you take the parts that you want, make that STL file, that mesh version, and that can then go right into that same workflow that we've been talking about all morning to make the 3D printed model. So this is kind of more my world. So I don't deal a lot with actual patients. I deal a lot with making things kind of on a chip or in a dish or in vitro, or all those terms of art. And so 3D printing is very useful for that. So there are ways that you can actually directly 3D print materials that cells and tissues can interact with. So this is a really cool paper where they use this really cool 3D. So this is a 1 millimeter scale down here. So this is a small little like alveoli of a lung that they 3D printed, that you can flow cells from a dish and actually line all of these sort of 3D printed vesicles with endothelial cells and grow kind of this like mini vascular network. And this is modeling that lung alveoli. So this actually can inflate and deflate with air to be like a model of a lung in a dish. That's kind of what I do for heart cells. So I use 3D printing to not necessarily directly print model like the cells and material for the growing of the cells, but print kind of like unique geometries that I can put heart cells into to then do things like stretch them or pressurize them to understand how those mechanical stimuli affect cardiomyocytes and heart cells, and also infect them with bacteria to have a model of septic bacteria getting to a heart. There are printers that can directly print cells. So you can grow cells up in a dish. You can mix them with one of those specialty gels. Again, we're getting more niche because they're not necessarily, we can't melt them, so they can't be high material. So usually we're looking at like different chemical reactions to go from liquid to solid. But these kind of suspensions of cells, and then just like all the other technologies, talk about kind of layer by layer basically draw out tissues that are like, collagen or other bioactive materials with cells inside of them. People always ask, can we 3D print organs yet? And I have to tell them not yet. But 3D printing is enabling things like, this is a cool paper that I found where trying to get better skin grafts. So the hand has a very specific set of geometry. And so it's very hard to like graft skin onto it. So these folks had created basically like a 3D printed mold to grow skin cells on, but then eventually this would sort of fit like a printed skin graft glove as opposed to having sheets. And then also an application where people are getting 3D printed components put onto them is, again, right, ears have a very complicated geometry, but thankfully like not a very complex biological function, right? So like the ear itself is mostly just, cartilage and looks a certain way and directs sound into us. And so there have been patients that have gotten these 3D printed ears that have cells that have grown on them from the patient and can actually get surgically implanted. So we're not yet printing hearts or livers because those have a lot of different types of cells and functions inside of them. But we can kind of use that pro of 3D printing to create these complex geometries. Like an ear that can have at least kind of like the basic skin layer and aesthetic function of an ear and get implanted onto a patient. That'd be very hard to do without 3D printing.
I do have a question. With your particular application, we hear you've got something planned to go up to the space station. Is that right?
I do have something planned to go to the space station. Yes, thank you for reminding me. So what I have is, again, in 3D printing. I don't make the piece. I need more 3D printing. I used 3D printing for the prototyping, and then used kind of like a molding type technology to make the final version. But 3D printing was very key in the initial prototyping of it. As I create these kind of, I should have pulled a picture. That's the one thing I forgot when I was prepping. Basically, like I have this sort of 1 centimeter by 1 centimeter soft chip, I call it, made out of like a flexible material that is molded from what was initially a 3D printed part. It's made out of a soft squishy material that is compatible with cells. I put some proteins on it to make it sticky. And then I put heart cells into these wells onto them. So then I make these kind of arrays of 1 millimeter long mini heart tissues that are these beating cardiomyocyte rich tissues, heart tissues. And one of my applications of them, now that I've built out, aided by technologies like 3D printing, this kind of heart on a chip model, I'm looking at the effects of bacteria on those cardiomyocytes, so specifically streptococcal pneumonia, how it and through what mechanisms it damages heart cells. And so an interesting thing about space is when you send bacteria to space, those bacteria become much more virulent and damaging and active. So what we're doing is we're sending our heart cells to space. And then once they're up there, we're injecting bacteria into them. And the space environment is going to make those bacteria go way more wild than would appear on Earth. And what we're hoping is by kind of like amplifying the activity of the bacteria, we'll be able to measure or observe some specific effects of the bacteria on the cells that kind of would have been hidden here on Earth when we compare the tests. So they'll go up to space, they'll get infected with bacteria, we'll have the bacteria washed out and be allowed to kind of be sick for about a week. And then we'll put a preservant on the cell that will kill them, but it will kind of capture and preserve all the genetic and protein material. And then that'll get frozen, sent back to Earth. And then we'll do like this genetic analysis to see what was happening inside of the cells over those previous 7 days while they were sick, compared to sick cells on Earth and compared to healthy cells on Earth and in space. It's supposed to go up this summer. Space travel is unpredictable, so it's gotten delayed. So it could go up in August or September this year, but it sounds like there's a good chance that my cells aren't flying to space until next spring, which is okay. Gives me more time to prepare, I guess. So one day I'll my name, and hopefully there'll be a paper about what happens when we send these cardiomyocyte cells to space to be infected. But that's again kind of this tissue engineering world, is like using the technology to create a thing to allow cells and tissues to be grown in a dish in a very particular form, function, and geometry, and then do experiments with them. So that's kind of my role. And just quickly, I think this might be one of my last slides, is there is a budding world of 3D printing pharmaceuticals, like drugs. And again, it's kind of trying to use the world of like personalization and customization to apply to create things that would be more difficult to create with classic tablet press and stuff like that. So there is one product on the market that is 3D printing that I found that kind of uses 3D printing to create a very unique kind of dissolving profile of the drug to kind of help it get delivered in the right time frame. But there are people proposing kind of using 3D printing to have tablets that are mixes of different materials, where like, kind of different formulations and all the different parts of it could be released or dissolved at correct timing. I've seen some cool work trying to use 3D printing to like aid with like accessibility. So you can make forms of drugs that have, like braille letters on them. So anyone visually impaired could like use the customized feel of the drug to recognize it. So there's not been a ton of commercialization of these pieces other than that one example that I found, but there's definitely still this growing world of research on trying to find how those pros of 3D printing in customizing and unique geometries and things like that can overcome kind of the cons of like the slowness of it all, right? Because when you're making drugs, you're probably trying to make thousands of them per minute. So you do run into other tools possibly being better. But yeah, so those are kind of my 3D printing in medicine examples. For some further reading, so I gave you some software recommendations. I gave you some links to tutorials. I really like this particular book, the 3D printing handbook. It's just like a very kind of like straightforward, like list and decision tables say like, these are all the types of printing, this is things they're good for, this is limitations, etc. Here are like the number one things to like think about when you're designing for this printing. So for further reading, I do recommend this book. I've pulled some stuff of it from my slides, the 3D printing handbook. It might be out of print in a physical form, but the Kindle version of it, I think, is only like $20. In fact, they have the digital version of it that I refer to a lot and really like it. But I think that's it. There's been some great questions throughout, but if there are any more, I'm happy to answer them. There might be something else in the chat. Let's see.
I did want to point out to the group here that if you want to get some hands-on experience with one of these, Micro Center has a great section. Kind of to the left, if you go in the store and go to the left all the way back where they have the toy area, if you've been in there recently.
Before you get to the Apple.
Yes, before you get to the Apple section in the back on the left, that room before that is filled with 3D printer stuff. The machines, the plastic,
That's very cool. And so now you can go and you say, that one's filament and that one's fused filament and that one's a resin printer and that one's vat polymerization. You're armed with knowledge.
I'm sure people will demo it to you,
Yeah, very cool.
Mark's, organizations, there's several around here, and they all have 3D printers.
True, yeah.
But they have you need an expensive one.
Dallas Makerspace, I think.
Yeah, Makerspace.
Yep.
I definitely know there's an active Dallas makerspace. I'm involved with the makerspace here in Birmingham, so there's a network, and we all follow each other on the social media, so they're always up to a lot.
What's the best way to learn Fusion 360? What's the best way to learn to do Fusion 360?
I really recommend finding a tutorial set that you like. The ones that'll be in the link, and I'll send Richard these slides so he can disseminate them to anyone that wants them. The really best way to learn is just by doing. And so whether it is, that kind of 30 days of learning, it looks like he has, like one lesson per day that you can do. They seem to be relatively well produced. But I think if you can just find someone whose instruction style you can handle on one of those online tutorials, just start working through them is really the best way. Anything else? All right. Well, again, sorry for my 15-minute tardiness, but I'm glad we got to make it work. I'll send slides, and that'll have my contact information. I'm always happy to try and answer questions that I can. But yeah, thanks for having me.
Yeah, and we'll get this posted on the webpage under the recorded section.
All right. Well, have a good rest of your weekend.
Okay, thank you.